Lab 2, Newton's Second Law and Drag Force, by Carter Young. The objective of this experiment is to determine the effect of drag force acting against gravity on a falling piece of crumpled up paper. So as you can see, I held the crumpled paper as high above my body as I possibly could and dropped it. Force of gravity pulled it down, and the force of drag acted up against the paper. I used my body as a reference point, setting the length bar to 1.88 meters. So some important information about this experiment. The reference bar used in the tracker video was set at 1.88 meters, which is the height of my body. The mass of the crumpled up paper was approximately 4.15 grams. Total displacement was negative 2.146 meters. So the distance from my hand being held above my head to the floor wound up being 2.146 meters. Total time was 0.733 seconds. The system includes the crumpled up paper. The axes had positive x to the right, negative x to the left, positive y up, and negative y down. There are a few physics concepts present in this experiment. The first involves Newton's second law, where velocity final equals velocity initial plus F net over mass times the change in time. F net in this experiment is actually the force of gravity minus the drag force. Drag force obviously acting in the positive y direction, and force of gravity acting in the negative y direction. The force of gravity is equal to negative mass times gravitational force acceleration, which is 9.8 meters per second squared. The drag force is equal to negative b times the velocity final. Negative b is a constant that varies depending on the shape of the object. Certain shapes give more air resistance than others, resulting in different b values. And so the net force in this experiment will be the force of gravity minus the drag force. So for my Python code, first thing I did was I set the ball's mass equal to 0.00415 kilograms. And then I said the ball position initial vector is 0, 0, 0, and initial velocity is vector 0, 0, 0 at t equals 0. So initially the ball is at an origin point and there is no velocity. Delta t I set to 0.0333 seconds, which was the time step that was used in tracker. I set the acceleration due to gravity equal to 9.8 meters per second squared, and the unit vector for j hat I set as 0, 1, 0. And then I said while t is less than 0.8 seconds, which is the time at which the ball hits the floor, weight is equal to the negative mass of the ball times gravitational acceleration times j hat vector, meaning that weight is acting only down in the y direction, and said that net force is equal to weight. Then, to predict the new velocity, I said the velocity of the ball equals the initial velocity of the ball plus F net over the mass of the ball times delta t. And as this runs, it calculates it, and I did the same thing with position. So after making the modifications to the Python code, I then ran the program. As you can see, the ball goes down, accelerating. So as time moves forward, the displacement grows greater and greater per period of time. The problem with the last computer model was that it only included the force of gravity, where drag also plays a force upon the object. So I went down to the bottom of my code and said F net is actually equal to the weight plus the force of drag. Weight in this situation being defined the same as earlier. Force of drag I defined as b times the magnitude of ball velocity times j hat. However, because there was no b value given for a piece of crumpled up paper, I had to find it myself. So I ran the program over and over until it gave me a displacement that was equal to what tracker gave me as my displacement. And so that was how I found the constant. Then to find the aeroscale, which gives an accurate representation of the magnitude of the arrows of drag force and gravity, I took about 2 meters, saying the displacement equal to 2 meters, and divided it by the weight of the object, which was which came to about 0.04067 newtons, which gave me an aeroscale of 49. Then I ran my code. As you can see, the ball falls a little more slowly than it did before. Drag force is the blue arrow acting up, and gravity is the yellow arrow acting down. So what happens is eventually the drag force will get to the point where it's the same as the force of gravity and the object will stop accelerating. After running the model with and without drag, I extracted the data points and plugged them into Microsoft Excel, comparing them with the tracker. As you can see, the model with drag much more closely fits the data from tracker than the model without drag. So the results. Does the computer model fit the data? Yes, but there are small discrepancies. These could be due to the paper ball not being fully compacted, air can flow into the cracks, increasing some drag force. What does this mean? Acceleration due to gravity is opposed by increasing drag force. Eventually, drag force would equal the force of gravity, preventing further acceleration, in which the object would have reached its terminal velocity. The computational model that includes drag force will predict terminal velocity if it's allowed to run longer. In this experiment, the object did not reach terminal velocity, did not go far enough. If the object was thrown downward, however, terminal velocity would not change. The only difference in this situation is that the object would reach terminal velocity faster. However, terminal velocity with the same velocity.